Hello and welcome to our new session of applications to molecular orbital theory to benzene molecule. Well, that is the new situation where we are talking about a polycarboxylic kind of system. In the earlier videos, we have discussed about the basics of group theory in molecular orbital theory, the basics of Huckel molecular orbital theory, so-called part 2, and resonance energies for cyclopropenyl cation in terms of the classical quantum mechanical calculations and in terms of group theoretical calculations. In the present video, we are taking this cyclic system to illustrate how the resonance energy can be computed without actually using a detailed quantum mechanical calculation and using an alternate method of group theory. I'm your instructor, Saurabh, and let's begin to work. Benzene molecule is a very classical and flat molecule. It has a point group of D6H. And if we take D6H as a basis for obtaining the 2-pi reducible for this particular case. So in D6H system, we see there are a large number of molecules, including identity 2C6, rotation of 3-fold, 2-fold, inversion center, improper rotations, horizontal plane of reflections, dihedral and vertical planes of reflections. So there are large number of codes. There are the symmetry operations. In terms of pi orbitals, if we consider the pi orbitals as the basis, we'll find that for identity, they are going to be 6. But if we talk about the other operations, the rotational operations, because all the vectors are getting shifted, except the C2, which contains actually in a line which is perpendicular to the principal axis, that is -2, the inversion goes to 0, the improper rotation goes to 0, the horizontal, because now it is completely inverted, so all pi orbitals are getting inverted to -6, so you get -6 here. For dihedral plane, they contain at least 2 bond vectors, and for vertical plane also, there are no vectors shifted. So these are the values of the 2-pi reducible using a so-called D6H character table, which is of course a very long and a huge character table. These values can be decomposed using the standard direction formula, and it has been found that when you do it, you get A2U plus B2G plus E1G plus E2U. This is quite consistent with the idea that A is one dimension, B is one dimension, and E is two-dimensional representation. So you had 1 plus 1 plus 2 plus 2, that makes it 6. That is, there are 6 representations in this particular case. The above result can also be obtained by recognizing that the rotations of p-pi orbitals about the principal axis can only be basis for us. Symmetry properties are determined by the rotational subgroup C6 only. Consider this figure. There are 6 pi orbitals, so you can consider either the entire C6 group, D6H group, but instead you would like to go for a C6, a rotational subgroup, and that is sufficient to work out in the present case. However, character table for C6 pointer group looks like something which contains an exponential value, which epsilon, that gives the e to the power 2 pi I upon 6. The I is of course under -1, that is a complex number. So here we have A, B, E1 and E2, and in terms of obtaining the basis for pi of orbitals, because there are 6 pi orbitals that remain unshifted, you get 6. But when you talk about a C6, it drops to 0. Every bond vector is shifted for C3 because it is collinear with the C6, it also 0. C2, which is collinear with C6 axis, is also 0. C32, which is collinear with the C6, is collinear, and C65 is of course 0. So very interestingly, what we see is the identity is the major contributing factor and the rest of the elements are 0, and if you decompose them, of course, you will find that the result is something like this: A1 plus B1 plus E1 plus E2. So all of them have come once in our picture. You have A plus B plus E1 plus E2. And this is very interesting. Since each rotation shifts, the orbital characters are 0 except for that for E. This is a result that can be obtained for any ring size of the molecule, irrespective of any size or the number of carbon atoms. We can demonstrate this. For benzene, it is because you are using C6, you are getting the each irreducible representation once in that particular wave equation. So also note that the result 2 phi can be obtained by adding the characters of the irreducible representation of the rotational subgroup that we have seen. and because the rest of them are falling to zero, so they are contributing nothing. The only contribution is coming from this side. If you all add them all one, you get 6. That obviously gives the result. So very conclusively, we can put a remark that in a cyclic system of type CHN, the rotational symmetry, if we consider Cn, there will be always n pi molecular orbitals, one belonging to each irreducible representation of the group Cn. You know very well that we have taken sigma bonds as a basis, a sigma bond framework as a completed framework, and we are ignoring it completely. We are only talking about the pi molecular orbital system in this particular case. In terms of D6H point group, we have seen that they are A2U, B1G, E1G, and E2U representations. That is more or less same thing. So you can simply go on doing the next job. The next job is to use the projection operations for a particular wave function. Say, for example, if you talk about for A, 2U symmetric species, you have projection of A for phi 1 that goes to character of identity, and character of identity followed by or multiplied by E operated on phi 1. Similarly, character of C61 and C61 operated on phi 1, and so on. So each time when we are taking the phi 1, so for rotational subgroup, we have to take all of them into account, and because all of them have the value of unit 1 value, so 1 phi 1 plus 1 phi 2 plus 1 phi 3 and so on is the final result in this case. So your equation is actually coming out something like this: phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 6. We can similarly carry out more operations, more projection on various systems like A, B, E, etc. And we can develop more number of equations. So the use of the set of characteristics of the operations of the coefficients of LCO above. This is applied to all cyclic or carbocyclic systems containing with a procedure. We get these 6 wave functions. How come? For psi 1, we get this. For psi 2, we get this. Phi 1 minus phi 2 plus phi 3 minus phi 4 plus phi 5 minus phi 6. You just look at the character table for C6 and multiply the components. Similarly, for other things, you have epsilon values. So phi 1 plus epsilon phi 2 minus epsilon phi star phi 3 minus phi 4 minus epsilon phi 5 plus epsilon star phi 6, and similarly for psi 4 you have phi 1 plus epsilon phi star phi 2 minus epsilon phi 3 minus phi 4 minus epsilon star phi 5 plus epsilon phi 6. As far as the E2 is concerned, it is also going to generate 2 equations. We have seen in the character table of C6, phi 1 minus epsilon star phi 2 and so on and so forth, and similarly this is the value for the set of psi 6 equation. So in general, we have now the 6 equations at our disposal, but the point in the last 4 equations is they contain the number epsilon, which is also subject to an imaginary complex number. Now it's quite easy to eradicate them if add or subtract them so that we get independently new equations. So convert the wave functions adding E1 and E2 into a linear combination with real coefficients. That is quite easy. So when you add psi 3 and psi 4, you get something like E plus E star epsilon. Similarly, the other values are also containing epsilon star plus E and so on. Fortunately, this falls to 1. That is what we will be doing is that we'll be assuming that if you're adding this, E plus E star is equal to 2 cos 2 pi by 6, that is equal to 1. And when you're talking about E minus E star, that is 2 sine 2 pi by 6 upon I, that is equal to root 3. Actually, if we are using these values, then we are close to generate equations of the kind. For psi A, of course, all the wave functions are positive, phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 6, and its normalized form would be 1 by root 6. For B, it is the plus minus going alternatively. So again, it's also 1 by root 6. As far as the even A is concerned, that becomes 1 by root 12 that we have seen. That carries a complex value. So 2 phi 1 plus phi 2 minus phi 3 minus 2 phi 4 minus phi 5 plus phi 6. Similarly, for psi even B, it is phi 1 plus phi 2 minus phi 6. And for E2A, that is again the even A type, but numbers have different values, positive, negative. 2 phi 1 minus phi 2 minus phi 3 plus 2 phi 4 minus phi 5 minus phi 6. And finally for 2B, it is phi 1 plus phi 1 minus phi 3 plus phi 5 minus phi 6. So these are the 6 new equations that have been generated using the expression that we have developed. What we have done is so far that we have used a character table for C6 point group, and we are getting the 6 equations correspondingly. To remove the epsilon, we have added 2 equations and subtracted 2 equations. So correspondingly for E1A, and we are getting the equations. As far as the solution is concerned, now we know that because it contains A, B, E, and E. So A1 plus B1 plus E1A and E2B and all. So that means you have one-dimensional, 2-dimensional, and 2-dimensional block factorization should be seen, and therefore our equation, it drops out something like this. So for A2U, you have H11 minus E. For B1G, H22 minus E. And for E1G, it's a 2 by 2 determinants. And for E2U also, it is 2 by 2 determinant. And of course, the rest of the elements should be 0. So if you independently take them, they are going to be equal to 0. So for H11 minus E equal to 0, H22 minus E equal to 0, and similarly H33 minus E, H34, H43, H44 minus E, H55 minus E, H56, H65, H66 minus E is equal to 0. So we have the kind of the method that we have developed, that here you are getting one value of E, one value of E is going to give 2 values of E, and this is also giving to 2 values of energy. So we have altogether 6 values of energy for benzene molecule as a whole. The thing is, we have performed the earlier also that we can use all the equations to obtain and solve the integrals, and we are not going to do it now. But instead, what we are going to see is that we are getting the various values, and these values are something like this. Now we are not interested in actually developing all that kind of thing. You can examine by yourself. We have 6 solutions. We have alpha plus 2 beta, alpha minus 2 beta for the first and the second solution, and similarly 6 pi electrons we can develop as energy scale of this kind. We have 1 alpha plus 2 beta, that's the degenerate orbitals in this case. You have alpha plus 2 beta, there are 3 bonding, that is the degenerate molecular orbital. This is 1, 2, and 3. And with alpha minus 2 beta, they are also degenerate. Where we are getting the 6 values of energy, and all the filling of 6 electrons would have been something like this, 2 starting from the ground state, and it finally reaches to the excited states respectively. And if you solve for 6 electrons, you have 6 alpha plus 12 beta. That gives you simply, if you take 6 into common, alpha plus 2 beta. That way, the energy in the system for delocalization or resonance can also be obtained. Only thing is that delocalization energy that we assume is that it is equal to energy of delocalized form minus energy of localized form. And when you talk about the energy of localized system, what we need to do is simply, very simple, the energy of the localized systems corresponding to the energy of an etheric bond, it times the number of pi bonds. So as many as pi bonds are there. So for example, if there are 6 pi bonds, we have to simply multiply it by alpha plus beta. So if you have 6 pi electrons, you have 6 alpha plus 6 beta, and so on. So the benzene molecule, it is there 3 times the energy of etheric pi bond. The pi bond energy for etheric molecule is given by 2 alpha plus 2 beta. Hence, for benzene molecule, the energy of localized system comes out to be 6 alpha plus 6 beta. And if you are interested in finding the difference of the delocalized and the localized pattern, that comes out to be eventually 6 alpha plus 8 beta minus 6 alpha plus 6 beta. Obviously, the answer is 2 beta. So the resonance energy for benzene molecule is equal to 2 beta. That is how theoretically the Huckel molecular treatment has predicted. Group theory has made an additional contribution, has avoided the kind of mathematics that is involved there, and we are now approaching to an indirect method coming to the same result. The rest of the things are now history. We know that experimentally it is found to be minus 18.2 36 kilocalories per mole is the resonance energy of benzene. So beta corresponds to something like 18.2. Beta is inherently negative, so beta must be equal to minus 18.2 kilocalories per mole. So this is how we proceed to the same values, same functions, and these are the figures which display the nodal planes in various systems according to our equations for molecular orbitals that we have developed. For psi, this equation, all are positive values, therefore there is no nodal plane. But if we talk about this is alternating plus and minus, you can find out the nodal planes and nodal surface, etc. For other values also, like psi E1A, psi E1B, you just notice these structures and compare with the equations you will find that it's quite easy to demonstrate the nodal planes or nodal points in a structure that has been developed for benzene molecules. So this is a general method. Even it can be applied to any carbocyclic system where you have a CHN kind of, whether it is 4 or 6 or 8 or 10, depending upon the Huckel's treatment. However, the Huckel suggests that the aromaticity would come for only those molecules which have resonance energy compared to, compared to other systems. In benzene, it comes out to be 2 beta, and therefore it is known to be the aromatic compound. So-called 4n plus 2 pi electron would get established. Thanks for watching now this video, and I hope you can develop an idea with this video to associate group theory in making quantum mechanical calculations easier for such systems. Thanks again.